Welcome to another deep dive. We're going to be talking all about heat transfer today.
Yeah.
Heat transfer, so you sent over an introductory chapter
Yes,
from a heat transfer textbook.
Yeah.
And this is going to be fun.
it is.
So let's just jump right into it.
Absolutely.
What is heat transfer? I always get it confused with thermodynamics.
Yeah, that's a common one.
Yeah.
Thermodynamics is really about the energy changes in a system.
Okay.
So how much heat is absorbed or released during a reaction, for example.
Okay.
Heat transfer is more about how that heat actually moves.
Okay.
So how it travels from a hot object to a cold object.
Gotcha.
So it's the kind of the motion
okay.
of that
so
energy.
Not just the energy itself, but the energy
Exactly.
as it's moving.
It's the action part
Okay.
of the story.
So how does that work? How does that happen?
Well, there are three main ways: conduction, convection, and radiation.
Okay. Let's start with conduction. Conduction is like when you're holding a metal spoon
Right.
over a flame and it travels up the handle.
Called that conduction.
So is that
Really?
like molecules bumping into each other?
Yeah, it's like a chain reaction at a very, very small level.
Okay.
The hot molecules are kind of jiggling around and they bump into their cooler neighbors
Uh-huh.
and they transfer some of that energy. And
Okay.
it just keeps going on down the line.
Gotcha.
And this happens not just in solids, like a spoon, but also in liquids and gases.
Okay, so what about convection? Convection copia. The textbook mentioned something about a boundary layer.
Yes. So think about like a cup of hot coffee cooling down.
Okay.
It's not just the air molecules kind of randomly bumping into the cup.
Okay.
It's also that the air itself is flowing.
Right.
And that's carrying heat away, and that's convection.
Okay.
And so the boundary layer is this kind of like a zone very close to the surface of the cup
Okay.
where the air is being heated up.
Uh-huh.
And it starts to rise. And then cooler air comes in to take its place.
Oh.
So it's like this little kind of dance of hot and cold air right next to the surface.
So convection is all about like fluids,
Yes.
like air or water
Exactly.
moving.
It has to have fluid motion.
Okay.
And there are actually two types of convection. There's forced convection,
Okay.
which is where we use like a fan or a pump to force the fluid to move.
Okay.
And then there's free convection, which is where the fluid moves naturally just because of density differences.
Right. Like if you're boiling water, hot
Exactly.
water rises.
Yes. Or like a plume of smoke going up from a fire.
Gotcha.
That's free convection.
So now for the weird one, radiation.
Yes.
So this is how we get heat from the sun,
Yeah.
even though there's no air in space.
Exactly. Radiation is totally different
Di-
from conduction and convection because it doesn't need any matter to travel through.
Wow.
It's pure energy traveling in the form of electromagnetic waves.
Mm.
And every object with a temperature above absolute zero actually emits radiation.
Wow.
So even you and I right now, we're emitting radiation.
So we're like walking radiators.
Yeah, in a way.
Okay, so we've got these three ways that heat gets around: conduction, convection, radiation.
Mm-hmm.
But how do we measure or predict how much heat is being transferred?
Well, that's where those, what are called the rate equations come in.
Okay.
So they're basically like mathematical tools that let us calculate how fast heat is flowing.
Okay.
So for conduction, we have something called Fourier's law.
Okay.
And that tells us that the rate of heat transfer depends on the material's thermal conductivity
Okay.
and the temperature difference across it.
So something with high thermal conductivity, like metal,
Exactly.
will transfer heat much faster than wood.
Yes, that's why you use a metal pot to cook on the stove.
Right.
Right? You want that heat to transfer quickly to your food.
All right.
And insulation works the opposite way. You know, you're trying to slow down
Right.
the heat loss.
So what about the rate equations for convection and radiation?
Yeah, so for convection, we have Newton's law of cooling.
Okay.
And that takes into account the fluid velocity
Okay.
and the temperature difference between the surface and the fluid.
So the faster the air flows over a hot object, the faster it will cool down.
Exactly. That's why blowing on your soup helps
Helps
to
to-
cool it down.
Makes sense. And radiation.
Yeah. Radiation, we've got the Stefan-Boltzmann law,
Okay.
and that one tells us that the rate of heat transfer depends on the object's temperature
Uh-huh.
and a property called emissivity,
Okay.
which is basically how well it radiates energy.
Okay.
So different surfaces will radiate energy differently.
Okay, so these equations help us predict how much heat
Yeah.
is being transferred.
Mhm.
But in the real world, it's rarely just one,
Very rarely.
is it?
It's usually a combination
Yeah.
of at least two, sometimes all three.
So the textbook gives us some examples
Yeah.
of this. Let's go through a
Sure.
couple.
Yeah.
So the first example 1.1, is an industrial furnace wall.
Yes.
So we've got this giant
big
furnace. It's got walls made of fire clay brick.
Uh-huh.
And we want to know how much heat
All right.
is escaping.
It's all about minimizing heat loss.
Right.
To make the furnace run more efficiently.
So are we talking conduction, convection, radiation? What are we talking here?
Well, in this case, we have to consider both conduction through the brick itself and convection from the outer surface of the wall to the surrounding air.
So it's like a two-pronged attack.
Yeah, you've got heat trying to escape in two different ways.
So we'd use Fourier's law for the conduction.
Exactly.
And then Newton's law
for the convection.
For the convection.
Yep.
To figure out how much.
And then you combine those together
to get the total
heat loss from the furnace.
What about the example with the steam pipe?
Ah, the uninsulated steam pipe.
Yeah, uninsulated steam pipe. So this one, I think, involves both convection and radiation.
It does. So I've got this hot steam pipe.
Okay.
And it's losing heat to the air around it through convection.
Okay.
But it's also radiating heat to the cooler walls of the room. So you've got those two things happening at the same time.
So we use Newton's law for the convection and then Stefan Boltzmann.
Exactly.
To the radiation.
You got it.
Add those together and we get the total heat loss.
Yeah, it gives you the big picture.
Why is that important?
Well, if you're designing a system that uses steam pipes, you need to know how much heat you're going to lose.
Right.
So you can account for it and make sure the system runs efficiently.
Right. So you're not losing all your energy.
Exactly. We want to keep that heat where it needs to be.
Okay. What about this heated rod example?
The heated rod, yeah. So this one's a little bit different.
Okay.
We've got electrical current flowing through a metal rod.
Okay.
And that generates heat within the rod. And so we need to figure out how the rod's temperature changes over time.
Okay.
As it heats up and as it loses heat.
So it's like a little heater?
Yeah, like a miniature electric heater.
Okay.
And so we have to consider conduction within the rod itself.
Okay.
Convection from the rod's surface to the air, and then radiation from the rod's surface to the surroundings.
Okay, so we've got all three.
All three happening at once.
Happening at once. How do we even begin to analyze that?
Well, that's where this idea of an energy balance comes in.
Okay.
I think maybe we should save that for the next section.
Yeah, let's take a break.
Okay.
And we'll come back and we'll talk about energy balances.
Sounds good.
Sounds good. Okay, so before the break, we were talking about how heat gets around conduction, convection, radiation.
Yeah.
Now, what about these energy balances?
Right. So energy balances, it's kind of like accounting.
Okay.
But for heat, we want to make sure everything adds up.
So what are we adding up? What are all the pieces?
Well, we've got the energy that's stored within a system.
Okay.
And that's where we talk about things like sensible heat.
Sensible heat?
Yeah, sensible heat is basically the heat that we can feel.
Okay.
You know, if something feels hot to the touch, that's sensible heat.
Makes sense.
Then you've got this other kind of heat called latent heat.
Latent heat.
Which is a little bit more sneaky. It's the energy that's tied up in phase changes.
Phase changes?
Yeah, like when ice melts or water boils.
Okay.
That's latent heat.
So it's like hidden energy.
Yeah, it's like hidden energy. You don't necessarily feel it as a temperature change.
Okay.
But it's there.
Gotcha.
So we've got the energy that's stored within the system.
Okay.
We also have to think about the energy that's flowing in and out of the system.
Okay, so that's all the conduction, convection, and radiation.
That's right. That can happen through all those different mechanisms. But it can also happen through work done on or by the system.
Okay.
Like, if you pump up a bicycle tire, you're doing work on that system, and some of that energy actually gets converted to heat.
Yep.
That's why the pump feels warm.
That's interesting.
So we've got energy stored within the system. We've got energy flowing in and out.
Okay.
And then there's one more piece to the puzzle.
Which is?
Energy generation.
Energy generation. What is that?
So energy generation is when other forms of energy are converted into heat within the system itself.
What?
The textbook gives a good example of this with resistance heating, like in an electric heater. So you've got electrical energy being transformed into heat, which then warms up the room.
Gotcha.
And, you know, this energy generation term, it can be positive or negative depending on whether heat is being produced or absorbed.
Okay, so it could be going either way.
Yeah.
So we've got energy stored, energy in and out, energy being generated.
Exactly.
And we're making sure
it all balances out.
It all balances.
That's the key. That's the whole idea of an energy balance.
And the textbook gives some really cool examples of this.
It does.
Like, for example, how the human body
yes, thermoregulation
regulates its temperature.
It's remarkable how our bodies can stay at that constant temperature even when the environment is changing.
Yeah. That is pretty amazing.
It's like we're walking, talking thermostats.
So this example focuses on heat transfer through our skin and our fat layer.
Right.
And it talks about two different situations.
Yes.
One where the person's just in still air and one where they're submerged in water.
Yes, and it's interesting how the dominant heat transfer mechanisms actually change depending on the environment.
Oh, interesting.
So like in still air,
Yeah.
we have to consider conduction through the skin, convection from the skin to the air, and then radiation exchange with the surroundings.
Right.
But when you're in water, radiation becomes negligible.
Okay.
Because water absorbs radiation so well.
So our bodies are constantly
adjusting, yeah.
to keep that temperature.
Exactly.
98.6.
It's a delicate balance.
Wow.
And, you know, it all comes down to these different processes like sweating, shivering,
Right.
that help regulate that internal temperature.
That is amazing. It makes you really appreciate how intricate and well-designed our bodies are.
It does, and it really shows how important it is to understand the different modes of heat transfer and how they interact in all these different situations.
Absolutely. Another example that I thought was really interesting was the one about using liquid water for cooling in fuel cells.
Yeah, that's a good one.
Especially in cars.
Uh-huh.
So fuel cells are interesting because they convert chemical energy directly into electricity.
Yes.
But they generate a lot of heat in the process.
That's right. And managing that heat is really critical for efficiency and for preventing damage to the fuel cell.
So this example focuses on like a specific challenge, which is preventing the water in the cooling system from freezing.
Right, especially in cold climates.
Right, in cold climates.
You don't want your fuel cell to turn into a block of ice.
Yeah, so this is a good example of an energy balance.
It is. It uses that energy balance approach to figure out how long it takes for a block of ice to melt if it's exposed to a certain temperature. So we're tracking the heat flow into the ice and how that heat is being used to change the ice's state from solid to liquid.
So these examples are really interesting because they show how all the stuff that we've been talking about is not just some theoretical concept.
Right.
It's actually being applied to real-world problems.
It has huge implications for designing and optimizing all kinds of systems.
Exactly. So speaking of designing systems,
Yes.
the textbook outlines a specific methodology for tackling heat transfer problems. Do you want to talk about that now?
Yeah, I think that would be a great way to wrap things up.
Okay, let's do it. All right, so this methodology for tackling heat transfer problems, where do we even begin?
Well, the good news is it's broken down into 7 clear steps.
7 steps. Okay, I can handle that. What's step 1?
Step 1 is all about getting organized, figuring out what we know. The textbook calls it known.
Okay, so like gathering all the information, right?
Yeah. Exactly. We lay out everything the problem tells us, what the system's like, what materials are involved, temperatures, any boundaries, the whole shebang.
So we're not just rewriting the problem, though.
Nope. Got to be concise. We want the essential info, the key players.
Gotcha. What's next?
Step 2 is find. Here's where we figure out what we're actually after.
So, like, what are we trying to solve for?
Exactly. Is it a temperature, a heat transfer rate, a specific flux? Got to know the destination before we start the journey.
Makes sense. Step 3.
Step 3 brings it to life. Schematic. Time to draw.
Ooh, I like this step.
Right. Visualizing helps a ton. We sketch out the system, label everything, dimensions, materials, all that.
If we're using energy balances, this is where that control volume goes, right?
You've got it. That and errors showing how the heat's moving, conduction, convection, the whole works like a map of the energy flow.
Love it. Okay, step 4.
Step 4 is where we're honest with ourselves. Assumptions. No model's perfect, right?
So we're admitting what we're simplifying.
Exactly. Maybe we assume things are steady, not changing over time, or that heat's only moving in one direction. Makes things easier to handle.
But we got to be careful not to oversimplify.
For sure. It's a balancing act. Simplify enough to solve it, but not so much we lose the important stuff.
Makes sense. All right, what's step 5?
Step 5 is properties. Think of it like gathering ingredients for a recipe. We need the data, the numbers, thermal conductivity, specific heat, all that.
So got to get those right, or the whole thing falls apart.
Precisely. Just like a good chef, got to be accurate with what we're working with.
Okay, bring on step 6.
Step 6 is the exciting part. Analysis. This is where the big guns come out.
The first law of thermodynamics, all those rate equations.
Got it. Setting up our equations, getting ready to solve. But the textbook says do the analysis first before plugging in any numbers.
So see the relationships between things before getting lost in the numbers.
Exactly. Keep the big picture in mind.
Okay, last step, what's number 7?
Step 7 is comments. Take a breath, look at what we got.
So, like, do our answers make sense?
Yep. Any limits to what we did? What did we learn? It's a chance to reflect, draw conclusions, maybe even think of what more we could explore.
I love this methodology. Really breaks it all down.
And to see it in action, the textbook uses the example of curing a coating on a plate.
Oh, right, using an infrared lamp.
That's the one. Got radiation from the lamp, convection from the air, maybe even some conduction within the plate itself.
So multi-mode heat transfer.
Exactly. And the example takes us step by step through how to solve it. We gather all the knowns, the lamp's power, properties of the coating, air temperature, all that. Then we clearly state we're looking for the plate's temperature, specifically the curing temperature.
We'd sketch the system, show where heat's flowing, then make our assumptions like steady state to keep it manageable.
Then we round up those properties, things like the Stefan Boltzmann constant for the radiation part. Finally, the analysis, setting up our energy balance for that plate.
Heat coming in from the lamp, heat going out via convection and radiation, use those rate equations, right?
You got it. And we want to express all that in terms of the plate's temperature, because that's what we're after.
So solve the energy balance and boom, there's our temperature.
Exactly. And this example even shows how changing the airflow, which affects the convection, can change the curing temperature too. Pretty cool stuff.
Wow, this deep dive has been amazing. We've covered so much. How heat moves around, these energy balances, those rate equations, even a whole problem-solving plan. I feel like I can actually think about heat transfer now.
That's what we like to hear. And honestly, we've just scratched the surface. There's a whole world of heat transfer out there waiting to be explored.
Well, you've definitely sparked my curiosity. Thanks for taking us on this deep dive. I'm excited to keep learning.
The pleasure's all mine. Keep those questions coming and keep that curiosity burning.